It is my distinct pleasure to introduce to you Dr. Daniel Ferris, number 558 from the University of Michigan. And Dan will be talking about robotics to enhance human performance.
Thank you. Thank you very much for the invitation. I'm looking forward to talking to this audience because this isn't my usual scientific conference that I come to, and it's nice to reach out a little bit across different disciplines to try to bridge that divide that still remains for many of us in our home units. So you don't have to look very far at all to look at examples in movies or science fiction or literature to find situations where people are envisioning how robotics can enhance human performance. Here's 4 different pictures from Iron Man, the Avengers movies, Tom Cruise in Edge of Tomorrow, Matt Damon from Elysian, Cyborg from the upcoming Justice League movie. All of these are examples of how we might enhance human performance with robotics as it advances and we merge it with humans. Starting out with just robotic exoskeletons, which would be under the same category as Iron Man or the Edge of Tomorrow or Matt Damon, there are an awful lot of devices that are currently out there being tested from different companies and from different research university laboratories. This is a good time for me to disclose that I work with Lockheed Martin and Exobionics and NASA, and also Adicept Technologies on exoskeleton technology. So if I say anything about their products, take it with a grain of salt that they give me money to talk with them about their products. But there are an awful lot of devices out there because the robotics technology has greatly advanced. The computer processors are much faster. The actuators are much more powerful and smaller. The batteries are getting smaller all the time. As a result, we can actually build things today that just 5 years ago seemed out of reach. And as a result, there's a lot of devices, robotic exoskeletons, that can assist human motion. Many of these devices are intended for individuals with disabilities, whether they have a stroke or a spinal cord injury, like Rex Bionics, Exobionics, Parker Hannifin, the Rewalk. All of those are intended for individuals with disabilities, but there's also a large research and development in the area of human performance augmentation exoskeletons. So things like the Raytheon exoskeleton, Lockheed Martin, Honda, these are intended for able-bodied individuals to give them capabilities beyond human capabilities at present. To give you a feel for this, because many of the people that I talk with in kinesiology haven't seen these in action, I'm going to play a couple of videos to give you an idea of what they look like. This is one of the first ones, the Hulk, Human Universal Load Carrier. It was created as a spin-off from UC Berkeley, Hermione Kazerooni's laboratory. It was founded as Exobionics. Originally Berkeley Bionics, they changed to Exobionics. And Lockheed Martin is now trying to develop the technology for military use. And the idea is this is something a soldier could wear for walking, for running, and carry heavy backpack loads through the mountainous terrain of Afghanistan so that they don't have to end up with all sorts of back injuries and fatigue as a result of carrying the heavy backpacks. One of the things that's universal in the business world of building a robotic exoskeleton is that they have trendy videos that will end up on YouTube because a lot of it is about marketing. They want people to see it, to have the buzz about what they're doing, and there's a whole lot less actual hard data on how well they work. Trying to find out measures of performance, of metabolics or muscle activity or biomechanics is really hard to come by when it comes from a company because they don't want any negative press about how well it's not working.
This is the Exos 2, the kind of closest thing we have at this moment to the Iron Man suit.
This was a spin-off from University of Utah, small company Sarcos, which has now been bought out by Raytheon.
Incredibly strong, and the interesting thing is It doesn't feel any different if you put 150 pounds on the back or if it's unloaded.
And again, you'll notice
The
the
Exos
trendy
2 is
music,
more
the
fluid
nice
and
video,
stronger.
the promotional quality of the...
I don't feel the strength, but I know I can pick up more. The big deal is that it takes a lot less power at the same time as it's stronger.
We reduced the power consumption by 50% by comparison to Exos 1, and our target is 20% of what Exos 1 used. We wanted to basically reduce power consumption to make it more practical for non-tethered use.
If you push on the board, like, I'm never going to be able to break that, but then you wind up and do it, and away.
This is
Suit HAL, or
probably the
hybrid
biggest
assistive
commercial
limb,
success so far.
allows its user to easily lift a 40-kilogram duralumin case, like this. Now, look what happens if an elderly person who has been bound to a wheelchair wears the suit.
She walked smoothly. It's amazing. I was surprised.
All of these things, it's really hard to find the scientific data on them, but invariably when you do find some scientific data, most of them aren't working nearly as well as the companies would want you to believe. There's a lot of them that are still in testing and refinement, but there's not many people with kinesiology skills that are testing them and figuring out, are they actually aiding the person to use them? And in fact, when we've tested them and other kines labs have tested most of these devices, the one thing they are is a very expensive exercise equipment. They drive your heart rate way up, they increase your metabolic cost, they're very difficult to use, so it's almost that you're putting them on not to help you move, but actually to get a good workout. And we need better controllers to interface between the human and the machine so that that's not the case. The one thing that people say when they wear these and they walk around in them is it feels like you're walking through molasses or honey. There's a lag time between the robot trying to know what you're doing and then moving with you. So it creates impedance with your initial motion, and then you get momentum and then it moves with you, and then you have to stop and you work against the robot again. So there's a lot of fighting between you and the machine right now. We don't have really good controllers that allow that to move in a very fluid and coordinated fashion. And so one of the things we've been working on over the last 15 years has been building our own controllers with our own robotic exoskeletons. And these companies won't let you hack into their controllers and use their hardware. So you've got to build your own hardware if you want to test a different controller out. And so most of what we build in the laboratory is about not a commercial product. We don't want something that we're going to have a company and sell. It's that something we want to test out a different strategy or do a different motion and try to figure out from a basic science standpoint, is this really going to help somebody out and how can we measure it? What are the benchmark metrics that we want to suggest people in the engineering domain want to use? We've built a number of devices over the years for the hip, for the knee, for the ankle. A lot of times we use these. They're called artificial pneumatic muscles. They're like specialized balloons. You pump air in them, they get short and fat. You let the air out, they get long and skinny. Extremely lightweight, produce high mechanical power, but they have a limited range of motion, just like your own muscles. Your muscles don't work like electromechanical motors. They don't shorten forever until they get down to a small size. They have a working range that they can generate force, and in the same way these artificial pneumatic muscles do. What's really nice about them is you can put the pneumatic pressure regulator off of the person and just use tubes to go to the individual to provide the compressed air. So you can keep the exoskeleton very lightweight if you're going to use it in a laboratory or if you're going to use it in a clinic with patients, because all of the weight can be put on a cart beside the individual. One of the controllers that we like the best over the last 15 years that we've tested is called proportional myoelectric control. And it's essentially using the normal physiological pathway. When you want to activate a muscle to do something, you send an electrical signal from your brain to your spinal cord down to the muscle. That electricity activates the muscle and you get the muscle contracting. We intercept that at the level of the muscle with an EMG, and then we send it through a computer, produce a little bit of signal processing on it, and then we send it to a pressure regulator to get contraction. So this is what it looks like in action. This is one of my grad students with EMG electrodes on the soleus. This is an oscilloscope with muscle activity showing up in the screen, and then undergrad is holding off an ankle exoskeleton off to the side. When you activate your muscles, this responds in the same time period. The electromechanical delay between when you generate the electrical signal to your muscles and when the exoskeleton responds is the same order of magnitude of your own muscles. It's on the order of 30 to 50 milliseconds. So our first study many years ago at Michigan was to take unsuspecting undergraduates that were intact, good nervous systems, and see how they respond to all of a sudden making their ankle super strong.
It's recording.
And I'm going to turn the power on at 5, 4, 3, 2, 1, on.
So it almost knocks her off the treadmill. She's going to a Aquinas gait. She's stepping on her toe. She's getting too much torque and power out of her ankle that she's not used to it. It's like if in all the comic books, if you come down and you made somebody super strong, yeah, they'd be really uncoordinated. They wouldn't know how to control that much power. We've made their ankle super strong all of a sudden, and that doesn't make sense to them from a motor control standpoint. It takes practice. Most individuals, it takes on the order of 30 to 45 minutes to learn how to walk again. So here's this same individual 30 minutes later as we turn it off. Notice she looks perfectly normal here.
5, 4, 3, 2, 1, off.
She has a short step, and she's walking left to right all over the treadmill, and she makes the comment,
"Wow, your leg feels heavier."
Wow, your leg feels heavier. Because what happens in that 30 minutes is you learn to turn the muscle activation down from that one muscle. All the other ones stay fairly normal, but that muscle needs to be inhibited. And when we take it away, all of a sudden you feel very weak. It's very similar to the sensation I've heard from astronauts when they come back. They turn down the activation of all those muscles because that's what they need to move around. And when they get back to Earth, they feel very weak. It takes longer for astronauts to adapt back because we're only changing that for about 30 minutes. It usually only takes 2 or 3 minutes before you're back to normal. And the more you train with these things, you can actually adapt on the fly. I've worn these in ankle and knee and hip and exoskeletons that I can adjust in one step now because I'm used to walking in them and I can go back. It's that motor adaptation, that motor memory that you store and you put it in the context, oh, I'm putting on the exoskeleton, control it this way. We've tested a large number of devices over the years. There are some basic principles. The more complicated the exoskeleton, the longer it takes to learn. If it's bilateral versus unilateral, it takes longer. If it's knee and ankle versus just ankle, it takes longer to learn. But we have a whole suite of kinesiological methods to study how people adapt to these. So we will have our robotic intervention, ankle, knee, or hip, or whole leg. We will walk them on a forced treadmill or a forced platform to get their ground reaction forces and their kinetics. We'll measure their oxygen consumption and carbon dioxide production. We'll film them to get their kinematics. We'll use EMG to get their muscle activity. We can stimulate their peripheral nerves to get reflex modulation with H reflexes. And then we even now can put electrodes on your head to measure your brain activity using EEG. All of these methods are almost all of the methods are very foreign to an engineer that's designing these devices. They understand how to design the robotic end, but from the standpoint of measuring actually if a person's doing well with the device is not as easy for them. And so what kinesiologists have a unique opportunity for is to work with engineers and figure out how do we make these devices better? Are they working? What can we do for different types of controllers or hardware? And let's make measurements. Another example from our laboratory is we built a running exoskeleton a number of years ago. Paper just came out this year in Journal of Applied Biomechanics. But essentially, it's a big carbon fiber leaf spring with another carbon fiber spring in a backpack that goes through a Bowden cable to your knee. A Bowden cable is like the brakes on your bike. It's a cable that allows you to push on a handle and get the effect at the wheel. Here we have storage of elastic energy that's transmitted to this component. When you put this on and you run, it accomplishes what we had intended. We wanted to say, if you have a knee injury, you want to learn to run again, but you want to reduce bone-on-bone contact forces in the knee joint. Can we reduce those joint contact forces? Can we reduce muscle activity in the quads? This serves that purpose, but when you measure metabolic activity, it actually goes up by about 40 or 50% because you have extra mass on your limb, and now during the swing phase, you're carrying extra weight. And that acceleration required for that extra inertia is what leads to an increase in iliopsoas muscle activity, makes it harder to run. So if you wanted to make this more successful, then you would go to a powered hip to assist this so that you could benefit the knee as well as not put extra work on the hip joint. We work with Lockheed and NIH and NSF funding to basically test a whole suite of different controllers. And I think really, kinesiologists understand biomechanics and energetics and motor control. And this is a great opportunity for people to really venture and collaborate with engineers in a way that's going to be coming very quickly. The market for robotic exoskeletons is rapidly expanding. Multiple consulting sites place it growing over $4 billion within the next 10 years. It's going to quickly accelerate. We need kinesiologists involved in this to help make these devices better. One example, Fortis is trying to figure out how they can market their device. And because the controller was so unsuccessful and it was making it so hard to walk and run, they came up with the idea of basically stripping all the motors off. So what they have is a frame that goes around you that's great if you want to stand in one place and carry a heavy object. There are lots of industries where you hold very heavy machine tools all day long while you're at work, whether you're grinding on a ship or whether you're using other metalworking tools. And instead of your arms having to carry it, they actually lock it right into the exoskeleton, which lets you walk around, work what you need to do, but the weight is actually being borne by the ground because it goes through the exoskeleton. That's a very small niche market, but it's one they can exploit now with the capabilities of exoskeletons. I don't think they would have realized that if they didn't do a lot of work figuring out why the other devices weren't working. The first exoskeletons on the market aren't going to be Iron Man type devices that do everything. They're going to be small niche devices. Another good example is one of my former grad students, Greg Sawicki, who's at NC State University, had a paper in Nature last year where they took our ankle exoskeleton device, took all the motors off it, and they just put a spring and a clutch on it. And if you build it very lightweight and with a nice clutch, what you end up doing is you store and return elastic energy just as your own Achilles tendon does. It's like a mechanical Achilles tendon to assist you, but the clutch doesn't require your muscles to activate to get the storage. And when you time it just right, in this paper, they show that if you can get the right stiffness of the tendon, so here on the x-axis is different exoskeleton spring tendon stiffnesses. If you get the right stiffness, not too stiff, not too compliant, he calls it the Goldilocks stiffness, then you get maximal return energetically and you actually reduce energy costs 7% compared to not wearing it. So if I measured you walking a mile, and then I measured you walking a mile with this, your energy cost goes down 7%. Some people would say, 7%, what's that? Imagine wearing a backpack all day with 7% of your body weight. That actually you're going to feel and you're going to notice. It's not going to be immediate, but it's going to build up over time. And if we can find ways like this to actually help people out with small niche uses, it's going to have a chance in the market. So I usually give this slide to my class, and unfortunately, almost everybody has no idea who these people are. It's very sad. But I used to watch this show all the time, and I thought it was very cool. And it was one of the reasons why I got interested in biomechanics, is because I want to understand, what leads to performance like this. And I thought back to Jamie Summers and Steve Austin, and I thought, why can't we take what we're doing with exoskeletons and actually do them on a prosthetic? And it turns out there are a lot of prosthetics on the market. Because of the robotics technology rapidly advancing, there are many companies that have these powered devices. The controller is still the problem. Even though you can get work out of these actuators on the mechanical device, how does the prosthesis, the artificial leg, know what your brain wants to do? And it basically tries to figure out from sensors that this is what your pattern is, and then move along with you. So there's always this lag. And you can't do something like walk through a crowded subway where you want to step left, step right, go big step, small step, because it's expecting from the last step how much it should power for the next step. So trying to think of how we might take advantage of the normal physiological path that we use to control our muscles, we decided, can we get muscle activity out of the residual limb muscles? So on amputees, they actually still have the calf muscles. What usually ends up happening, for instance, in a transtibial amputation is they take the calf muscles, they wrap them around the end, and they tie them off. They're still there, but they have no ankle to control. So we put electrodes on the skin to show, yes, they actually still have muscles. They still have volitional control over it. If I measure them inside the socket, there are tricks that you can do to actually put a little buffer between the electrode and the socket so you can get reliable signals. But the longer that they're amputated, actually, the more abnormal those signals become. Because they actually don't control an ankle anymore, they become very erratic or non-normal from a muscle activity standpoint. Some of them just may disappear because they don't do anything, and so there's next to no activity during a gait cycle. Other ones end up doing new functions. Some of the amputees learn to tighten up their socket right as they're coming off the ground so that instead of pistoning effect, the muscles are all tense right as they're coming off the ground, and it helps pull the socket up. So they get a muscle activity pattern that's very different and abnormal compared to an intact individual. But we wanted to see if we could use these signals as a way to control robotic ankle. Again, even though you can buy these devices, they won't let you hack them. They won't let you put your own controller on their hardware. So we built our own. This, again, is using artificial pneumatic muscles, plantar flexors and dorsiflexors, with a little cage skeleton that goes around the normal socket, and then a ankle joint that just moves in free motion. It really doesn't take much money to build this. It doesn't take much engineering know-how. The people that could build these were undergrads in the lab with enough knowledge, because it's parts that you spend dollars on, not tens of thousands or hundreds of thousands of dollars. And it lets us test the idea, if I put this on an amputee, do they learn how to use it? Here's one of our subjects.
That's cool. All right.
In this control setup,
Oh my gosh.
she
Don't
has
fall.
volitional control of her ankle. If she wants to
Wait,
go
turn
up on
to
her
the
toes,
side.
she can go up on her toes.
Yeah, go
If she
ahead.
wants to push off a lot, she pushes off a lot. If she wants to sit there and just move her
ahead,
ankle
go ahead.
back and forth, that's under her control. There's no controller on the market right now that can do
All right.
this. But it's a very physiological
Good.
controller, because it works in the
Okay.
same way that your nervous system works. We do have the limitation that we need that powered compressed air source, because with compressed air, it provides a high mechanical power output, and so it's not going to be portable. You'd have to wear a scuba tank on your back if you wanted this prosthesis to walk around the mall. That's not viable in the long term, but again, I'm not an engineer. I'm not there to build a new product. I'm trying to understand how humans move and use the technology to make it better. And so we publish papers, we write grant proposals, we study the kinesiology of using robotic devices, and then the companies come to us and ask us to collaborate because they want our insight to devise their better devices. One of the things that was really powerful for us, we have a qualitative study that's coming out. We wanted to know what these users felt about the experience. Not just the biomechanical measures, but their own interpretation of what it was like. And it was a pretty powerful response. And here's a couple of examples. It's about the same weight as the other. In this case, the other was another powered exoskeleton, powered ankle on the market. But it looks and feels more natural walking than the other. Once I figure out what it's doing, I can figure out how to operate it, and it picks up really quickly on what I want to do. Friday's session was extraordinary for me. Just the brief experience of moving a limb I had not had contact with since 1970 was a total treat. Picture Christmas for a 5-year-old. Very pure, great stuff. It most likely wasn't extremely obvious, but both my eyes were tearing. And I'm like, that's not your ankle. But they get that embodiment feeling because they're in control of when it's moving. and they see that visual feedback and the sensory feedback of moving their bodies when they want to. And they learn to control it, and they have a much greater embodiment of that device when they feel like they're in physiological control. One of my friends, Hugh Herr, who's a bilateral amputee, has walked on the devices. He uses his own. He has powered ones that he builds, and he basically put an EMG controller on it because he didn't believe me that it would work and that people would like it. And he said the biggest difference is, imagine riding in a car or driving the car. When you're driving the car, you know when you're turning left and right, and you're not going to get car sick. When you're riding in the car, if somebody's swerving all over the place, you feel like you're being thrown around. And even though you can see what they're doing, it comes a little bit late, and the relationship between the control and the motion is not as tight. And so I think there's going to be a big need for kinesiologists to take part in this, because we do understand the mechanics and the control and the energetics of how humans move. And in the future, as the technology gets better, more and more individuals will be using it. In particular, I don't think the electrodes buried inside the socket is going to be the long-term solution. You end up with sweat and dirt and dust, and becomes unreliable for long-term. But there's a lot of companies out there that have solutions. One of them is the implantable myoelectric sensors. So this is a electrode that's about the size of a big grain of rice that can actually be inserted into a muscle with a hypodermic syringe. And it's stationary for many years. They've already done human testing. They just got FDA approval. But you can take the electrical signals, send them through Bluetooth or Wi-Fi outside of the skin so that you don't have to go through the skin with a wire to the prosthetic that's around the foot. And in fact, just recently, OSER has advertised, had a press release of their first testing of this type of control with the EMG using these IMESs. They have one subject that they've actually started testing, and they see that as the future. Coming up in the end of this month, OSER and Otto Bach, two of the largest prosthetic companies in the world, are having a powwow meeting where they've invited 20 experts to come talk to them about the control of these prosthetics, and can we do something as a group, as a field, to try to move it forward. There's only one kinesiologist invited. I think it would be much more helpful if there were more, but they're in charge of the invitation list. But I think this is the sort of place where we have a unique niche to offer to the field. 3D printing is also creating a huge number of possibilities out there. So I talked about Greg Sawicki, my former student's passive elastic ankle exoskeleton. There are passive elastic upper limb exoskeletons for children. There are many children with disabilities that don't have enough strength to lift up their arms and to interact with their world. And as we heard earlier, there's a lot of the normal development that comes from interacting with your world and being able to move around and to move objects and experience that. These devices are being 3D printed for hundreds of dollars. They have rubber bands that allow them to counteract gravity, so they let these children actually move at a much earlier age and experience their environment. There's virtually no studies on how well this is working and whether or not there's changes in the movement quality or the long-term effects of using these. 3D printing is also leading to upper limb prosthetics for children. One of the reasons these work so well for children as opposed to adults is you get the strength advantage of being small. The smaller you go, materials are stronger relative to their weight. That's why an ant can lift 200 times its body weight. That's why if you watch the Olympics, the people that lift the largest percentage of their body weight are the smallest weightlifters. It's not the big 250-pound weightlifters, because you get a strength of size in the material when you go smaller. So when you're building a prosthetic for children, 3D printing actually works pretty well. And there's a lot of different nonprofit organizations that have blueprints to actually build these prostheses for children, and they give them for either free or hundreds of dollars to children that can't afford a prosthesis. Some of you may have seen this recently, but I'll play it just so that.
So we're just gonna go down here. We're looking for 912.
Hey, Alex, how are you? Pleasure to meet you. I have another bionics expert on hand, so I thought I'd drop by.
Thank you.
Yes, a pleasure. Nice bow tie, by the way.
Thanks.
How were your travels?
It's very good.
Well, I thought I'd bring one of my gauntlets and match it up with yours and see if everything's copacetic. You want to have a look?
Sure.
Ready?
Yep.
Great.
Each one looks the same.
Actually, I think yours might be better than mine. What do you say we both try them on, do a progress report?
Okay.
You know who that is?
Iron Man.
What's his name?
Robert.
Great. God, dude, it's even cooler than I thought. I'm having a technical glitch. As you can see, my light isn't working. Half the time, you know, I design one of these, it winds up breaking on me. But what I do is I keep working on it, kind of like you're working on it with Albert.
He keeps working and working until he gets it right.
Yeah, I think yours is still a little bit more right than mine because at least, you know,
The lights work.
your light works, yeah. Ah, look at that, Dan. It's a marriage of robotic technologies. Bang, nailed it. Love it. Hey, good job, Albert.
Thank you, sir.
Yeah.
Appreciate it.
Albert has made it so affordable. I'm probably going to start farming out a lot of my tech work to Albert, too. I feel like he could cut the price point down on one of my suits, which right now is, I guess, about, I don't know, $1.5 billion.
To UCF, that's my undergraduate alma mater. Albert Monero is a student, undergrad, that said 3D printing works really well. We know a lot about myoelectric control. Can we build a prosthetic limb for children very cheaply? And they can. They have a website at Limitless Solutions. You can download all sorts of different designs, print them out yourself, and they have a nonprofit that takes in money, helps put them together and send them out to children. We know nothing about how well they work. Can we build better controllers? The people that are designing them know robotics, but they don't know the human side of things. People that understand motor control, motor adaptation could greatly help them. So it's not just the biological side of kinesiology that is going to have to deal with this advance in robotics. One example comes from Oscar Pistorius, who is a bilateral amputee, who is a very fast runner. His specialty is the 400 meters. He's from South Africa. His best times are very fast. He wanted to run against able-bodied individuals in about 2008 and 2009, and he was outlawed by the IAAF. And the IAAF said, you know, we have a new rule that says people that have an advantage from elastic energy storage mechanisms cannot compete. And so they wrote it for Oscar because he was actually competing against able-bodied individuals and winning. They sent him to Germany, and they had a very biased set of questions they wanted answered. They made measurements. They outlawed him. He took him to the International Court for the Arbitration of Sport. They had a whole nother set of biomechanics experts study him, and here's some of the video from that. Peter Wayan, a number of people that studied him and tried to figure out. They basically took him to court and they got the right for him to participate. Whether or not he really has an advantage over able-bodied individuals is still really up for debate. There are some biomechanists that feel he does. There are some biomechanists that feel that he doesn't. But there's the social and ethical implications that are going to come around when we do have robotic devices that can put an amputee on the same standard as an intact individual. When do you say they can compete and when they can't? And those are things that are going to have to be dealt with. So, you know, my take-home message is that we really need kinesiology to work with engineering on these devices, because if we really want to get to the bionic man and bionic woman and robotic exoskeletons that can help individuals, whether it be soldiers or whether it be industrial workers, there's got to be this give and take, and kinesiologists have a responsibility to take up this charge and to work with them. They can't just bury their head and say, well, that's not what I do. We need people to do this. If we don't do it, there's always going to be other people that come along and decide, oh, I'll build my own stuff, and they may have nefarious purposes. So in the immortal words of Stan Lee, with great power, there must also come great responsibility. And I think as a field, as kinesiologists, we need to have a little bit more say in how things are moving forward with these robotic technologies, because it's not going to progress without us. And then just thanks to many of my grad students, postdocs, collaborators, and the funding sources. Thanks for listening.